Hello all, my name is Balaji and welcome to my YouTube channel. In this video, I'm going to explain about the working of YOLO algorithm which is used in object detection. So we'll see the theoretical understanding of YOLO algorithm completely from scratch in this video. And with that said, let's get started. Before getting into the YOLO algorithm, let us now discuss about the difference between classification, localization and detection. So to talk about classification, classification is nothing but labeling an image. For example, in this image we have a car and the image classification is nothing but we just label this as car. So we do not do any bounding box inside this. So this is generally called as image classification. To talk about localization, localization is also similar to classification, but one thing is we just draw a box around the image indicating where that particular classification is. So for example, so here this is again a car, but localizing the car with a set of bounding boxes and saying the car where the car is actually present. So this is what we call as localization. And to talk about object detection, so object detection is nothing but having multiple objects inside a single image, and we also do the localization. Or basically talk about this, the image classification and localization generally have one object inside them, whereas this object detection has multiple objects. So the object detection can be multiple things, like it can predict cars, the persons inside the image, and it can also predict any other vehicles like motorbikes. So essentially it can detect multiple objects inside one single picture, whereas localization is nothing but we just predict one single image and give their particular location where that classification is present, and image classification is just labeling an image. So this is what is the difference between localization, classification and object detection. Now that we have understood what localization, classification and detection is, let us now just talk about some of the parameters in this bounding box. So how this bounding box is actually defined. So basically what happens when we give the image, we also give the bounding box coordinates in order for our model to get trained. So after we give the image, we pass these images into a convnet. So this is a convolutional layer. So we call this as a convolution layer where we have the max pooling and all those image recognition things. And after this will be sent into a deep neural network, and we have the output layer here. So this is the output layer that we have, which basically has the softmax activation function in order to predict what are the classifications. Either it is a car, or we have the motorcycle, or we have a person. So these are the classifications that we will stick on to this particular video, and the softmax function will give us the predictions of whether the given image consists of a car, motorcycle and a person. But since we also need the bounding box in this, so we also have the bounding box coordinates as one of the inputs here. The bounding box coordinates for this car is nothing but the center of this picture will be the x and y coordinates. We call this bx and by. So this b is nothing but indicating the bounding box. So we generally have x as the input image and y as the output here. So just for the identification purpose, we give this as bx and by. And similarly, we also have the height and width of the image. So here in this case, we can take this to be the bh, which is the height of the image, and this can be bw, so which is the width of the image. So essentially, once a picture is given for training, it will contain the picture itself, and also it has the bounding box coordinates. So as we just spoke, the bounding coordinates are nothing but bx and by, which is the center of this object, and we also have the height and width of that particular object. So we can write bh and bw. So these are the four coordinates that we will also pass as a data to our neural network, so that it predicts for any image that's not in our data set. And these values generally take the values between 0 to 1. So essentially, the start of the image, this point, could be the 0 comma 0 point, and the ending point here could be the 1 comma 1 point. So in taking that in mind, let's now try to approximately calculate what bx and by will be. So x can take the value as somewhere between I would say 0.5. So x is 0.5, and the y can take a value somewhere between 0.6 or 7. So this is the center point, and the width of the height of the image is nothing but this is the height of the image. So considering the total height of the image to be as 1, we can safely assume that our BH is nothing but it takes a value like approximately 30% of this total height. So we can take the height to be as 0.3. So BH is nothing but 0.3, and taking the breadth of the image, so assuming the total breadth is 1, so this particular breadth of the object can be somewhere around 0.4. So these are just approx values that we are talking about. But when we pass these bounding box coordinates to the neural networks, those values will be exactly accurate, because we manually annotate all these labels and then send it to the neural networks. So now that we have understood how the bounding box coordinates work, let us now have a look like how the output variable y looks like. So basically we know that we have these three classifications in our data set, which is our car, motorcycle and person. And going forward, let us assume these notations as C1, C2 and C3, where C1 is nothing but the car, and C2 is the motorcycle, and C3 is the person itself. So now the y variable just looks like something like y is equal to, it is a vector which consists of these following values. It consists of a value called PC. So PC is nothing but which actually gives the value whether an object is present inside the picture or not, whether an object is actually there or not. So essentially there could be images which doesn't have any motorcycle or any car or person. So this PC value gives us whether these pictures are actually present, these objects are actually present in the image or not. So we can write whether a picture is present or not. So this is the value of PC. It takes values from 0 to 1, where if it is 0, there is no such objects inside our image. And after that, we have our bounding box coordinates that we saw in our last slide. So which is Bx, By, and we have the height and width of the bounding boxes, which is Bh, and Bw, which is the width. And followed by, we have these three values, that is C1, C2 and C3. Okay. So now, just taking this image as an example, we'll see what the y value would be. So taking this image as an example, the y value is nothing but y is equals to, we have now a PC here. So PC just indicates whether this image contains an object or not. So this image actually has an object that is in our classification, which is a car. So here the PC value will be 1. And the bounding box coordinates. So we have the Bx values, By value, and we'll have the Bh value as well as the Bw value. Now, when we actually see the C1, C2 and C3, so C1 indicates car. So this is actually a car. So C1 value will be somewhere around 0.96, indicating 96% probability that it is a car. And it also gives out the motorcycle value. So this is not a motorcycle, so its value will be very less. And the C3 value, which is not which is not a person, so the C3 value will be 0. And taking another example where we just have a empty road here, and there is no objects of our interest here. So which means we do not have a car, neither a motorcycle nor a person. So in this case, our y value will be something like this, where the PC value here, so it shows the object of interest is present or not. So here the PC value will be 0, and we really do not care when the PC value is 0, we really do not care about the other values. So this is how the y value will be. So these values are nothing but whatever the value be, we are not interested in it, just because it doesn't have the object that we are looking for, since the PC value is 0. Yeah. So this is how the output label look like. So it generally consists of the object of interest followed by the bounding box and followed by the number of classifications that we have in our data set. And to talk about the loss function is nothing but loss just looks like something like this. So we can give the loss as y. So assuming this is the y, so we can take this as y1, this is y2, this is y3, and y4, y5, y6, y7, and the final one is y8. So we have 8 elements inside this y vector. So to calculate the loss function, we can safely write it as y1 minus y1 hat the whole square, where y is the actual value and y hat is nothing but the predicted value, plus y2 minus y2 hat the whole square, plus up to, we have 8 elements in this, right? So we have y8 minus y8 hat the whole square. So this is the loss function if we have the y1 value to be as 1. So which means if we have an object, then this is the loss function. Suppose if we do not have an object, then we can safely write it as y1 minus y1 hat the whole square if y1 is equal to 0, which means if there is no object, we are not really considering the other elements in this image. So we'll safely assume that only this prediction is important to us. So this is how the loss function is defined. Let's now look at one of the main and important component of the YOLO algorithm. So given an input image like this, the first thing that YOLO does is it kind of puts grids on that image. So in this case, I've splitted this into a 3 by 3 grid, but essentially in the YOLO algorithm, we'll be having 19 by 19 grids. But for the understanding purposes, I just took the algorithm to have a 3 by 3 grid here. And what the YOLO algorithm does is it just applies the image classification algorithm that we saw earlier on each of the grid cell. So this is the first grid cell and the y value for the first grid cell. So for this grid cell will be like something. So the PC value here, there is no object of interest. There is no car, neither a motorcycle or a person. So the PC value here will be 0 and the all the other values are not of our interest. So we are not going to care about all these values. Similarly, the second picture also doesn't have any image, so the PC value will be 0 here, and in the third cell as well. So if we just see the fourth grid here, it kind of has a car which is of our interest. So the fourth image will have a Y value. So Y value that has the PC. So PC is 1 here, which means there is an object of interest, and followed by the bounding box coordinates, that is bx, by, and we have the height of the image, height of the object essentially, which is bh, and we have the width of the object, which is bw, and then we have c1, c2 and c3, where c1 indicates the car, right? So here the c1 value will be there, so which is 1, and the other values will be 0 and 0, because the other values are just motorcycle and bike, which is not present in that grid cell actually. And when you look at the next cell actually, so this cell also has a image of our interest, so that value will also be similar to something of the previous cell, and the other cells essentially do not have any images of our any objects of our interest. So this particular y vector would be of the shape 3 by 3, which is the split of the cell, so 3 by 3, and each y vector has 8 elements, that is 1 2 3 4 5 6 7 8. So 3 for the classifications that we have, and 3 and 4 for the bounding boxes, and 1 for the object of interest is present or not. So essentially we have 8. So this will just output 3 by 3 by 8 dimensional output. So 3 by 3, which is the cell, and it gives us the value of these vectors as a volume. So this is what I wanted to discuss about the output vector, and this is how the YOLO algorithm's core components work. But you can get a question, what if a grid cell contains two objects? Essentially, the YOLO algorithm is split on 19 by 19 grid cells, so it's much finer. So there could be a less chance of having two objects inside the same grid cell. But even when that scenario occurs, there is a solution to address that, which we'll talk about later in the slides. One other thing that we need to make a note of is that whenever we give the bounding box coordinates, right? If we take this car as an example here, the bounding box coordinates, the center of the car is a point somewhere here, and the starting point of this grid cell will be considered as 0, 0, and the ending point of this grid cell will be considered as 1, 1. similar to what we discussed earlier for an image. So this grid cell itself will be considered as an image, and this is the center of that object, and this is the height of the object, and this is the width of the object. So we can write here similar to what we saw before, like 0 comma 0 and 1. This is approximately at 0 0.5 comma 0 0.5. So 0 0.5 comma 0 comma 0 0.5, which is bx and by. And if we see the height and width, the height is around, I would say, 80 percentage of the total height, which is 1. So BH is nothing but 0 0.8, and BW is something of 0 0.8 again. I would write like 0 0.85 maybe. So these are the bounding box coordinates for this car. But if we take the second car, right? So the bounding box coordinates again somewhere lies between here for this car, and this is the starting point of this image, which is 0 comma 0, and this is the ending of this cell, which is 1 comma 1. And I would say the x lies somewhere between 0 0.7, so bx will be equal to 0 0.7, and by will be equal to somewhere around 0 0.5, and the BH, which is the height of the image, should be somewhere 0.6, because it almost occupies 60% of the total height, so we can give 0.6 here. And the width of the image is around, we could say it's around 0.8. But at times there can be a problem where the car can extend from this point, uh, and it can even move away from one particular cell. Similarly, the height can also start from here, and it can go beyond what is our grid size. So in those cases, the BW and BH values can take values greater than 1. But please do remember that the BX and BY values will always be the value less than 1, because the center coordinate can definitely lie within a cell, and which can be actually computed between 0 comma 0 and 1 comma 1. So the general understanding is that bx and by will take values less than 1, whereas bw and bh can take values greater than 1 if needed. Let us now talk about one of the interesting parts of this algorithm, which is intersection over union. So this intersection over union is one of the evaluating factors which determines how well is our bounding box being predicted. Say for example, in this picture, the orange box is our ground truth, which is the correct bounding box that we given for training. But this yellow bounding box is something that is being predicted by our algorithm. So how do we judge the performance, or how do we evaluate this bounding box did well or not? So that is being answered by the intersection over union part. So intersection over union is also called as IOU. So intersection over union is given by the formula area of intersection divided by the area of union. So the area of intersection here is nothing but the overlapping regions between these two boxes. So this is the area of intersection, and the area of union is the total area of both the boxes. Whenever the IOU value is greater than 0.5 or equal to 0.5, we consider this to be as a good prediction, or the bounding box is correct. If the IOU value is less than 0.5, then we consider that prediction as a bad prediction. Mostly the value is used as 0.5, but you can alter these values as 0.6 or 0.7. The more the IOU value threshold that you have, the more accurate the bounding boxes are. Let's now talk about the non-max suppression. So there is a good chance that one single car or one single object can have multiple detections by our algorithm. So similar to something like this. So essentially the YOLO algorithm uses 19 by 19 grid cells. So one car will itself be surrounded by multiple grids, and each grid will themselves think that that is the center point of this car, and that will give multiple bounding boxes for one single object. So we can handle this specific problem by the use of non-max suppression. For every object that is being predicted, we get the PC value whether this particular cell contains the object. So that will be outputted here. Say for example, this bounding box can have the PC value of 0.6, and this may have the PC value of 0.9, and this one may have the PC value of 0.7. So what non-max suppression does is it takes the maximum value out of these three, which is the 0.9. And similarly with this car as well, this can have the PC value of 0.7, and the center box can have the PC value of 0.9, and the outer box can have the PC value of 0.6. So now what non-max suppression does is it takes the highest value, and after taking the highest value, it kind of takes the IOU of this highest value box with the other bounding boxes. So with the other bounding boxes, if the IOU value is greater than 0.5, we are safe to eliminate the other two boxes. It is just because if there is a high IOU between two boxes, it is likely that they are trying to bound the same object, resulting in an unwanted duplicate box. So we can discard them. Conversely, if the IOU is low, then there is a higher chance that the box for different objects, since there is less overlap. So that is the basic idea here. So that is what we call as non-max suppression. So for the non-max suppression, we need to do the following things. First thing, we need to take the PC value, which is the highest, and we need to calculate the area of intersection. We need to calculate the intersection over union for the boxes, and any boxes that has a greater than or equal to 0.5, which is the high overlap, then we can safely remove those boxes. So that is the basic concept of non-max suppression. So the meaning is that the confidence with the highest value is always taken, which is the lighter boxes here, and the darker boxes here are removed. So whichever that doesn't have a maximum value, which is called the non-max, then those boxes are just eliminated. So this is the basic idea of non-max suppression, and ideally at the end we can get one high confident bounding box for our objects. Let us now talk about anchor boxes. So anchor boxes are used whenever we have one cell which has the midpoint and has two objects. So how are we going to handle this? Here, for example, this grid cell, the center grid cell has the midpoint which has both a person and a car. But the output variable that we have just has y is equal to PC, and the list of bounding boxes, which is bx, by, and we have BH and BW, and we have C1, C2, and C3. So in this case, we can get only the bounding box for one image, one object, but here in this case, we have two objects here. So how are we going to handle this particular situation? So in order to handle this, we are going to input a predefined set of shapes called the anchor boxes into our algorithm. So we are now going to input two anchor boxes, one with the shape which is narrower, and the other with the shape which is broader. So essentially you can have as much as anchor boxes that you can, but for this example to explain, I'm just taking these two anchor boxes. So this anchor box 1 is for the person, and this anchor box 2 is for the car. So essentially what we are going to do is that we are going to reshape our y into a different shape, like y equals to, now it becomes a bigger shape. So this again has PC, and it has BX, BY, and BW. It has BW, BH, and C1, C2, and C3. And similarly, this is for the anchor box 1, which is of this shape. And it again has PC, and BX, and BY, and up to C3, which is for the anchor box 2. So this is for the anchor box, and this is for the anchor box 2, and this is for the anchor box 1. So this is the general understanding that we should have. So for example, say for example, this is a person, and we have two anchor boxes here. So we have one box, which is the person, and we kind of have a prediction. Say this is the person, and this is a car which is being predicted. Then this anchor box actually calculates the intersection over union. It calculates the IOU, and whichever cell gets the highest IOU, that anchor box will be considered for our evaluation. For example, in this case, the person will have the anchor box 1 as the predefined shape, and the car will have the anchor box 2. So for a cell that contains both car and the person, so in that case our output variable y will be something like this, which has both car and the person. So the PC value for the first anchor box, which indicates the person, is 1, and it gives the bx, by, and bh and bw values. And similarly, it gives the confidence. Say for example, if c1 is the car, it gives 0 here, and if c2 is for the motorcycle, it gives 0 again, and if c3 is for the person, it gives 1 here. And for the anchor box 2, this grid cell again contains the car, right? So again, for the PC value here will be 1, and it outputs the bx, by, and it outputs the BH and BW. And similarly, there is a car, so the C1 will be 1 here, the other two values will be 0. So in this case, even when a grid cell contains multiple objects, we can define multiple anchor boxes, and we can get the multiple bounding boxes for that one specific grid cell which contains multiple objects. What if we use this kind of a shape, but we have only one anchor box? Say for example, we have only the person and not the car. So in that case, what happens is that our output will be something like 1 followed by bx, by, bh and bw, and it gives the output for the person because it contains only the person. If there is no car, then the PC value for car will be 0, and the other values are just don't cares, because we really don't care about the other values. At the end, we'll be getting the coordinates for the person. So in this case, what happens is that till now we saw the shape of y to be 3 by 3, which is the number of grids that we have, followed by 8, which is the number of elements in y that we had. But now we are multiplying that by the number of anchor boxes that we have, which is 2 here. So that is the shape of y that we are talking about. So this 2 is nothing but the number of anchor boxes that we used to have, and this 8 is nothing but the PC plus the 4 bounding box coordinates plus the number of classes that we have in our data set. And this 3 by 3 is nothing but the number of cells that we have in our data set. So this is the use of anchor boxes, but there are still some disadvantages that we can discuss about the anchor boxes. That what if we have two anchor box shapes, but a grid cell contains 3 objects? So in that case, the anchor box doesn't really perform well, and this is one of the limitations of this algorithm. And what if there are 2 objects with the same anchor box and a same grid cell center? So again, that is also one of the limitations of this algorithm that we need to keep a note about. Let's now have a quick summary of all the things that we have learned. So essentially, given an image, that image will be split into S by S grids. So essentially that is 19 by 19 grids, and for our example, let's take this to be as a 3 by 3 grid, and the y shape is given by the formula S by S by 5. This 5 is nothing but the PC and BX, BY, BH and BW. Again, this will be added with C, so which is the number of classes that we have, number of classes, and that will be multiplied by the number of anchor boxes. So this is essentially the shape of y that we are going to get. So for any image that we have, for example, this image we have only the car, so the y shape will be something like this, where initially for PC we have 1 because it contains an object, and let's assume that we have 2 anchor boxes, and the first anchor boxes is the shape of the car, and it outputs the bx, by and bh and bw values. And for car it's c1, so c1 is 1 and the other two values are 0, because we have 3 classes as an example in this video. And the second anchor box, there is no other objects in this, so that PC value will be 0, and the other values are essentially, we do not care about all those values here. So the neural networks actually output some random values here, but we are not interested on those values actually. So this is actually the overall output that the YOLO gives us. And finally we do the non-max suppression to avoid many bounding boxes for one single detection, and that is how we get the final output. And this video is just an overview for your understanding of how YOLO works. To get a better understanding and to dive deep into how every moving component of YOLO works, you need to look at the research papers. I've left those links in the description of this particular video, so you can have a look at those research papers. And thanks for watching. Meet you soon in another video.